We are about to start our main event, the current state, trends, challenges, and future of chips. I'm going to start with just a few notes and then bring the speakers up. So we're going to provide a little bit of context because we realize everybody's coming from a different background, and we're only going to have about an hour to go through a lot of stuff. So one, chips are everywhere. I'm dying to know the numbers you guessed for how many chips you own. I bet most of you guessed significantly low. There's over 1 trillion chips produced each year. The number of chips you have in your home is probably in the tens of chips, especially if you have a smart thermostat and a smart microwave and smart light bulbs like Philips light bulbs around your house and things like that. Just the number that are connected to the network is probably 20 plus in most of your homes. That's not even counting the number that are in your cars and places like that. You have lots of chips, not just the ones in your laptop and your desktop. There are great geopolitical tensions right now. U.S. and China are battling for global supremacy in every possible way, and chips are the key for many of these ways. And unfortunately, Taiwan is in the crosshairs as home to the best chip fab place on the planet, and we'll talk about that coming up as well. But there are tremendous geopolitical concerns around this technology topic. Supply chain resilience, or lack thereof, was really exposed in the pandemic. It was exposed in manufacturing overall, but we began to see the fragility of the supply chain for chips. And remember when we were seeing news articles about there weren't cars for sale. That was often because of the lack of chips available for those cars, other parts as well. But there's a very delicate global supply chain and ecosystem around making of chips. Advanced manufacturing is hard and expensive. These days, it can take up to $20 billion for a single fabrication plant. You can go start an AI software startup or services startup with just yourself tomorrow. Put up your Squarespace website, get the word out there, et cetera. I don't think I see anybody in this room that can start a fab tomorrow. Anyone got 20 billion that I don't know about? If so, we also have other giving programs for the Austin Forum. So it's incredibly expensive, and that's why you see large companies dominate chip fabrication. AI and machine learning is increasingly driving a lot of the revenue in this space. And we'll talk about CPUs and GPUs and AI-specific chips in the conversation. But a lot of what you're seeing in the press is about AI driving the market. Don't be completely fooled, right? There are still far more CPUs being made in the world, general processing chips of various scales and performance capabilities and such than accelerators. But the number of accelerators is growing, and the revenue from those is now tremendous in the data center space. There are growing environmental concerns, producing and all of the materials needed to make this tremendous number of chips. Remember, I said it's crossed 1 trillion chips per year. A tremendous amount of materials have to go into making those. And then where do the chips go? Well, a lot of them are going into data centers that are using 10, 20, 50, 100 megawatts of power. There's a tremendous carbon impact from that if it's not using green power. And you can bet that unfortunately, most of these data centers, not all, but most are not powered by 100% green sources yet. There are some notable exceptions and examples. There's a growing business in West Texas for wind-powered data centers and so on, but there's some tremendous environmental concerns about how the economy is so incredibly dependent on chips at very large scales. And then there's some security risks. And it gets back to the opening question. If you've got chips all around your house, what are the security concerns, not just in the software that's running all those, but even potentially creeping in to the chips themselves? How can things be hacked and taken advantage of? Some of the hacking techniques of recent years that have made it into the press have been flaws and things like speculative branch. Is that rain coming down? Wow. All right. That's cool. I like that. Speculative branch prediction errors in chips that had to be solved with some performance penalties in order to prevent the potential for cyber threats. So there's a lot going on in the chip space right now. And with that, I'm very pleased to introduce 3 longtime experts in this space. Please welcome to the stage the stage area, Michael Ignatowski, Senior Fellow at AMD, Eric Van Hensbergen, Fellow at ARM, and Thomas Fordorko, the COO of Inspire Semiconductor. Please welcome them, and let's grab the chairs. And I think we're going to blank the presentation for this part so we don't blind our speakers here. There you go. Yeah. All right. So I didn't give long intros for each of them because we have the intros on our website, but I did notice in doing this, and you all can have a seat, that two of them worked for IBM for extensive periods of time and another for Motorola. And as Austinites, you've undoubtedly heard of those companies because we've had big presence from IBM and Motorola. They've been tremendously important in creating the tech ecosystem that made it important for us to create the Austin Forum on Technology and Society. You've heard of two of their three companies now because two of those three are global leaders in semiconductor business. And Thomas, yours is going to be also next year, right? You all need to hit the buttons on your mic, by the way. There you go. All of them are involved in a number of initiatives around town. I'm going to give each of them 5 minutes to do a quick opening statement in which they'll introduce some more context about what they do and what they are most cognizant of in the chip sector right now, possibly concerned about, possibly excited about, et cetera. So we'll do 5-minute opening statements from each and then a 45-minute conversation. And Mike, we're going to have you start.
Okay, and I'll stand up a little bit here. I work at AMD Research on computer hardware futures. And when people ask me what I do, and I'm in a snarky mood, I say, I work on designing tiny, tiny little sand sculptures. I usually get blank stares, but I'm getting some chuckles here. That's good for the blank stares. Computer chips are made out of silicon. Sand is made out of silicon, so computer chips are actually made out of sand. And the circuits on them, you can think of as tiny little sand sculptures. Anyway, I'm going to do some quick background here and talk about 3 major laws or trends that have been affecting the industry for a while. There's Moore's law, Dennard scaling, and the lesser known second Moore's law. So Moore's law, I think most of you have heard of this. It's basically started with a observation from Gordon Moore, beginning of the integrated circuit industry, that the chips people are making seem to have twice as many transistors on them roughly every 2 years. And this was just an observation, but it quickly became a self-fulfilling prophecy. Everyone assumed their competition was going to follow Moore's law. So if they want to be competitive, they better invest to follow Moore's law too. Eventually, the meaning got changed a little bit they thought that computer performance doubled every 2 years, which is roughly true, but not exactly. And it's been slowing down a little bit lately. And I'll tell you some of the reasons why. So the second one is Dennard scaling, which people in the industry know, but a lot of other folks don't. It was an actual engineering law from the physics of transistors recognized by Bob Dennard. And he recognized that if you scale down the size and dimensions of a transistor and the voltage all the same way, the transistor works just fine. So if you shrink the width by a factor of 2 and the length by a factor of 2 and the height by a factor of 2 and scale down the voltage by a factor of 2, the transistor works just fine. In fact, it works better than just fine because it works faster and it's more power efficient. So the industry has been riding this for decades, literally, as the way to implement Moore's law scaling. Unfortunately, it's not perfect law. There's one thing it missed, and that has to do with leakage current through transistors. As you scale down transistor size, leakage current doesn't scale down. In fact, it grows exponentially, which is a problem if you know anything about exponential growth. You can't ignore it too long. And before long, transistors, instead of being on and off switches, started acting more like dimmer switches, which is not good. So they had to go to more fancy types of transistor structures. They introduced something called FinFET, and then something called gate all around, and there's a ribbon FETs coming up, and who knows what's after that. But this made things really expensive, trying to get things smaller and smaller and more complex at the same time, which leads us to Moore's second law, which was the observation that the cost of building a fab and equipping it roughly doubled roughly every new generation of technology. And it started off fairly cheaply early in the industry, like a $4 million to build a fab. But if you're familiar with what happens and you keep doubling things over and over again, you know this is going to be a problem. So $4 million to start. We now have pieces of equipment in modern fabs that cost over $100 million. Fabs themselves cost, as Jay mentioned, up to $20 billion. Not many companies can afford that. Most companies that design computer chips now are fabless. All three companies up here represented are fabless companies. We design the computer chips, and then we take it to one of the big fabs that produce it. And unfortunately, the world is now consolidated into just three companies that can do state-of-the-art computer chips. There's TSMC in Taiwan, which is a concern. There's Samsung, based in South Korea, and Intel, based in the United States. Now, Intel mainly makes chips for Intel. They try to bring other companies in and manufacture for those, but they're not doing very well at that. So as a result, they have a very high cost and they're struggling financially. And maybe in another 5 or 6 years, the industry will consolidate to just 2 companies in the world that can do this, neither of which is based in the United States. Now, the US government has been aware of this. 2 years ago, they passed the CHIPS Act, which puts about $280 billion into improving the US chip companies. And then Texas last summer passed what is essentially the Texas version of the CHIP Act, which also has a big pot of money to bring computer manufacturing into the state of Texas. And we can talk more about those later and see how effective they've been.
Thank you, Mike. Thank you, Mike. Thank you, Mike. Eric.
Okay, I'm Eric Van Hensbergen. As Jay said, I used to work for IBM Research. Came to Austin over 20 years ago to go join IBM Research, and then left IBM Research about 12 years ago, almost 12 years ago exactly, to join ARM. For those of you, well, more people know about ARM today than used to. And I'm going to talk to some broader industry trends, but just to make sure that everybody knows what ARM does. As Mike said, we are a fabless company, but even beyond that, ARM doesn't sell chips. So it's a bit weird to have me up here talking about chips, perhaps. We are essentially purely a design company that designs components, and we have an ecosystem of partners, actually including AMD, as well as several others, that take our components, put them together with their own components into an SoC design, and they then contract that out to a foundry to produce the chips. And that business model has been really effective for ARM because it's not our chips, it's Samsung's, it's NXP's, it's several other companies that I can't mention because they say we can't say their name and say that they do it. But 99% of cell phones have ARM CPUs in them. And an increasing number of laptops and automotive products and consumer electronics and sensors all have ARM-based products. We've shipped almost 300 billion chips since the company was founded. And ARM's been present in Austin since 2016. And there's close to 1,000 employees, and we're continuing to grow. And so it's great to hear about ACC engaging in workforce development because we all need it. It's really hard to find new folks in this industry, and this industry is growing like crazy still. So that's a little bit of background on ARM. But because of where we sit in the ecosystem as sort of as a design house for types of CPUs and lots of other different components that go in, we have to have a deep knowledge of the fabrication technologies, of the SoC technologies, because our designs have to adapt to all these different gate designs that are coming along, as well as topologies. So one of the outcomes of Dennard scaling, slowing down, is that companies have gone to new, interesting ways of continuing to get performance and efficiency. And actually, AMD was one of the first to really show how profitable it was, or cost effective, I guess I should say, which resulted in profits, of going to chiplet designs and looking at producing chips that stack on top of other chips and composing the silicon in different ways, because it's easier, for instance, and it's not easy by any stretch of the imagination, but it's easier to produce a 16-core chiplet and then combine a bunch of those to make a larger CPU than it is to make that larger CPU from the get-go. And that's why now, instead of transistor scaling being the thing that's driving performance in all of our devices, it's actually core count that's actually increasing the performance. And you now see systems from both of our companies anyways that have 64, 128, 256 core processors, even in the general purpose CPUs. And in GPUs, it's even denser compute. So that's another trend that's been coming in industry. But to date, most of chiplet technology has been sort of single company. So AMD produces chiplets, combines them with other AMD chiplets, and goes to a single fab that puts them all together. The chiplet economy is coming where you will have multiple vendors. There's multiple standards that are now in flight to allow companies to have their own chiplet that then could combine with an ARM or AMD or a RISC-V chiplet. And that's much more cost effective than if you had to build the whole thing yourself, even if you were licensing IP from a company like ARM. So that's going to drive a new economy in being able to customize chips and a new way of doing business. And that the initial phase of that's probably going to still be single foundry, but hopefully those same standards will evolve so that you'll be able to mix and match chiplets from different foundries and go to different packaging technologies. And that's one of the areas that the CHIPS Act that was mentioned is investing heavily into, is looking at some of these advanced manufacturing techniques, not just to kind of put these chiplets together like Lego bricks, but also to stack them in 3D. Including memory technologies, which is another huge driving area for semiconductors. Now, ARM doesn't do any business in memory, but all of these emerging workloads use much more memory and are much higher demands on bandwidth and latency. And that's where a lot of the true bottlenecks are, especially in AI. So when we talk about enabling AI, it's much less a story of CPUs, and it's more a story of interconnects and memory in order to expand performance in that particular area. And then one final thing that I'll talk to just as a piece of information, another area that I'm involved in is through SRC, which is Semiconductor Research Corporation, which is essentially a group that lots of companies, including AMD and ARM and Intel and a bunch of others, get together with academics and fund academics doing research projects. And the SRC has two really interesting outcomes in the last year that I helped work on. One of them was the decadal plan for semiconductors. And all of these topics and many more that are going to be important by 2030 are documented extensively in this decadal plan, and it's all free. So if you just Google SRC decadal plan, it's like a 200-page document covering reliability.
I think we have that link later in the slides.
Okay,
too.
great. Reliability and security and everything, and new use cases and all of those things. So it's a great resource for folks that want to learn more about this than we can cover today. The other related thing by basically the same group is the manufacturing and productivity technology roadmap, or manufacturing and packaging MAP-T roadmap, which came out also last year and was meant to inform, was commissioned by NIST and the US government to inform them in ways that they should be structuring funding from the CHIPS program. So that's another interesting roadmap to kind of read about what the challenges in this space are in achieving some of these advances in performance and energy efficiency and sustainability and workforce development. So both of these are great documents for good background in this area if you want to learn more.
Great. Thank you, Eric. I should point out, you may not realize it, but in developing these little micro sandcastles that Mike was talking about, the chips may use the same kinds of materials and the same overall processes, but there's a lot of magic in exactly what the sandcastle is that you're designing. In other words, how you're laying out the circuits on that silicon. And we have AMD here does it according to an x86 instruction set architecture. And Eric talked about how ARM doesn't actually make chips, but a lot of companies make chips using ARM's IP to make ARM-based chips like Graviton from Amazon in the data center down to Snapdragon in phones by Qualcomm. Our third speaker, Thomas Fedorko, is from a startup, not a global technology giant yet, and uses yet a different instruction set architecture and core type in the way they etch silicon. So with that, Thomas.
Yeah, good evening. Thanks. It's a privilege to be a part of the Austin Forum tonight. So yeah, I'm representing Inspire Semiconductor. We're a greenfield startup company here in Austin. We were started back in 2017. And our goal is to bring to market a supercomputer cluster of chips that will turn the HPC market upside down. So high performance compute, obviously a huge market. Data centers are going up everywhere. I think everyone understands and has at least a fundamental understanding of how much power it takes to drive these huge data centers. And so we looked at the problem and said, how can we provide massive amounts of compute horsepower at a significantly reduced power? And so that's the birthing, that's the birthright of Inspire Semiconductor. And so what we've done is we turned to the RISC-V architecture, which is yet another architecture, an open architecture. It was the right architecture for us for a variety of reasons. It offered incredibly high performance and low power capabilities. It's an open ecosystem. You don't need to, delve into proprietary software stacks, and you can run Linux on it. So our chip is self-hosting Linux, which obviously is very nice from a software developing perspective. And what Thunderbird offers right now is an extensive advantage on that power performance curve. So yes, it's RISC-V, and yes, it's a startup, but it's answering a lot of the problems in the market today. And because it's CPU based, not, everybody hears about AI and GPUs, and believe me, it's an incredible market space being served by some incredible technology. But if you need 64-bit floating point, which a lot of HPC workloads do, then you need to turn to a CPU architecture like Thunderbird has. And that's where we really shine, is in that market space where you need that level of math and precision. And the other nice thing is it's deterministic. So if you've got a financial workload that requires determinism all throughout your software, you got to get the same answer every time when you present an equation. You can get that on a RISC-V CPU-based system like Thunderbird. So it's a very exciting market space that we're tackling with some really creative solutions. Obviously, with 1,536 cores, you heard, hundreds of cores. We have 1,536 64-bit floating point cores on a single piece of silicon. So you can imagine the mesh fabric. We've had to get very creative in how we make all of those cores work efficiently with one another, but it solves a truckload of workload functions for a data center like application. And so we're putting 4 of those on a PCIe card, making them so you can slide them, undock your PCIe current solution and dock in our solution. And it's a very, very nice low power, high performance solution.
Great, thank you. All right, now I'm going to ask them some questions, and we'll have a conversation about some of the trends that we see right now. One of these trends, of course, everybody's heard of the phrase GPU, and probably most people don't even know what it stands for anymore, because the G used to stand for graphics, and it was all about video games. And now they take the graphics hardware out of the ones sold in data centers. They're using the fact that they happen to be really good at matrix operations, which is also what AI needs, not just graphics operations, but AI needs a lot of matrix operations as well. So we had some companies that have converted their GPUs to be used for AI accelerators. Couple of questions I have for you here that are related. Do you see this trend towards more and more of the revenue in the market shifting towards GPUs, or even AI-specific, new designed AI-specific accelerators? Or do you see the number of startups and the amount of effort going into building these accelerators gradually leveling things out? Because all these systems need CPUs, and then they add accelerators to them. So how do you see this balance playing out of the general purpose processors versus the GPUs versus very AI specific processors playing out in the next 2, 3, 5 years? And I know all of your companies, it's relevant to you, this question. So I'd like to hear from each of you on this, how your companies sort of are going to react to these changing workloads and the demands, as well as the supply demand economics of it.
So I'll go first. There's an engineering principle that when you design something and optimize it for a function, it works much better at that function than it otherwise would if it was a general purpose thing. That's why in a toolbox, you have separate tools for putting in screws, hammering nails, and sawing wood. You can make one tool that does all of those, but it just wouldn't be that good. So there are two basic needs in a market for accelerators. One is there needs to be a large market that will pay for them. And the AI market is now very large. It'll pay for special purpose things optimized for AI. And the other is that the technology growth has to slow down somewhat. So if you can design a special accelerator, but 2 years later, the general purpose CPU can do just as well because the technology improves, it's not worth designing that. But the technology has slowed down. The AI market is really big. So based on basic engineering, economic principles, yeah, you're going to see a lot of these accelerators come up. NVIDIA already has the vast majority of their profit coming from GPUs. AMD is trying to get into that situation. With any luck, we will.
The most powerful system in the world uses your accelerator technology, so let's not
They
underplay it.
They do. Thank you for pointing that out. The Frontier supercomputer at Oak Ridge National Labs uses AMD components. Yay. But it's not an AI system yet. And I'll turn that over to Eric.
Sure. So there's a lot of different dimensions here. Special purpose accelerators take a lot of different forms. So coming from an ARM-based perspective, we have so many different market segments that we target. All of our mobile products have GPUs in them as well. Your phone has a GPU in it. Now, it's not the big iron that's in Frontier or in a Grace Hopper NVIDIA supercomputer or in the supercomputers you're talking about, but it ends up serving a very similar purpose at a smaller scale. And why this is important is the big iron systems, the GPUs that require a ton of power in the AI world today, are being used to train AI models for the future. But how do those AI models get used, right? And so there's two sides to AI. There's the training component, and then there's the inference component. And the inference component is how the model gets used. So when you ask ChatGPT a question, that ChatGPT model trained for months on a supercomputer, but then it gets processed through an inference. And those two workloads have two very different sets of requirements. And some of it has to do with scaling. Now, there's all of us in the room here. We could all ask the same model a question, and it's got to serve out all of those answers. That's an inference. That scales out really nicely. That can even scale out to doing inference on your phone, for instance. And so having small GPUs and small accelerators is going to be just as important as having large accelerators. So that's part of the answer. It's sort of the same as Mike. You're going to see a lot of these, but you're going to see them in a lot of different flavors is the point. Now, the second thing is the catch-22. Yes, when you specialize something for a particular task, it's going to be better at it. It's going to be more efficient. It's going to run faster. It's going to cost a little bit more because you've specialized it. But worse is the programming problem. And this kind of gets to what our other speaker was saying, which is if you have a general purpose CPU, then the programming problem is a little bit easier. Software is portable to it. It'll run Linux. Linux doesn't run on GPUs, right? Nobody cares if they're running Linux except Linux geeks, but that's fine. I'm a Linux geek. But you can't, writing an application for a GPU is a fundamentally different thing than, or even an accelerator is a fundamentally different thing than targeting a regular processor. And that development cost carries with it a heavy weight. So if there's 100 new accelerators that get generated every year, that's 100 new programming models that developers have to learn. No software ecosystem gets built off of that. ARM's success as a company, as an instruction set, is that we're a standards company. We have an ISA that's a standard ISA that everyone can target. And there's a set of libraries and applications and tools that all target that. And x86 had the same thing before us, right? GPUs don't have that. NVIDIA has CUDA, AMD has ROCm. Other accelerators have other accelerator technologies. Some of them are abstracted like PyTorch and things like that. But those are all specialized things that have specialized targets on the accelerator, and that carries a heavy cost. We talked about the cost of fabs. The cost of producing chips out of those fabs is around $700 million to $1 billion, and a big portion of that is the software cost. And that's even worse for GPUs. It took NVIDIA billions of dollars to seed the CUDA ecosystem that programs their GPUs. So acceleration doesn't come for free, and software development carries a heavy cost with it. It doesn't mean that we won't have accelerators, but what it does mean is we need to mature the technology to a point where we can have standards around it, so we can have a common developer interface to these as opposed to proprietary interfaces, if they're really going to deliver on their promise.
Yeah, Thunderbird wasn't necessarily designed for AI. We in our next gen, we'll probably add some instructions that make it a little more adaptable into the AI market, but we are really good on the graph analytics side of AI. So if you're on the front end math side of AI, we're a really, really good solution for that. I think, again, as it's been noted a couple of times, the GPUs require some specialized software programming, and it takes loads and loads of time to learn it. A lot of engineers don't like it, but they learn it because that's what NVIDIA offers, and so they have to go learn it. Having an alternative to that is it's a smile on most software engineers' face. You tell them they can develop all of their software using Linux on open tools, using compilers that are openly available, and they tend to get pretty happy. So I think the beauty of having an open ecosystem is it just reduces the amount of overhead that's required to develop the software. And then that software is portable to other RISC-V platforms. So I think that's where RISC-V really shines.
Right. I'm going to do a little sync here for everybody based on what you've heard so far. I know some of you are in this industry and everything makes total sense to you, and others are still learning. So I want to make sure that we've done a little sync here before I ask the next question. So all of them have talked about etching things into silicon. There's a company called ASML that makes the extreme ultraviolet lithography equipment that does that sandcastle making and tiny features in silicon. These companies all decide what those features look like, but that company ASML then uses the ultraviolet lithography to do the etching. And then they've mentioned a few of the companies that can actually fabricate it, that can use that EUV technology to etch into silicon wafers. And what gets etched might be a silicon wafer full of x86 CPUs or AMD GPUs or ARM-based CPUs for the data center, or ARM-based CPUs for a smartphone, or RISC-V-based CPUs. So each of those silicon wafers that TSMC is doing this etching in using the ASML equipment might be for different purposes. Similar overall process, but the talent behind it, the IP that each of these companies have, is based on using that etching technology and that fabrication technology, and they say what gets etched and what makes it better for this job or that job or the other job. Mike mentioned at the beginning, though, that we're starting to see some limits there about how much further we can take this etching into smaller and smaller features. And what you've probably realized by now, and it's also in the picture for this event, is these silicon wafers are 2D. So what happens to keep up with Moore's law if we're running into limits and carving things smaller and smaller features in 2D wafers. And that leads to my next question. I hope I've got everybody caught up for this. There's been a lot of talk about 3D features and trying to add 3D features to what have normally been very 2D chips. Where do each of your companies stand on that? Are you doing anything in terms of logic design for 3D architectures for your processors?
Well, let me first make sure everyone caught what Jay was saying. We're down to 3 companies in the world that can produce state-of-the-art chips. Those 3 companies all depend on one company, ASML, in the Netherlands to produce the equipment for their state-of-the-art fabs. So that's the situation the world's in right now. In terms of 3D, yeah, it's something that certainly AMD is looking at a lot. We're starting to employ that in our chips. It's kind of a one-step benefit that once you do this, it gets a nice benefit, and then you have to keep doing it forever, and there's not another follow-on thing, except there is a one more step after that. Right now, we're designing essentially 2D chips that you stack together. There's another more complex step that says, we're going to design things that span 2 or more chips, like design a CPU core that spans 2 or more chips. And that way you can make it even more compact, tighter together. It'll run faster with lower power. So there's kind of 2 stages there where you can get some benefit out of 3D stacking. But once you do that, there's not much more to get from it. It'll have to be there for the foreseeable future, but you'll have to look at other things besides that.
Yeah, and this starts to stray from my area of expertise, so no follow-up questions on it. But there's also, even within those fabricating technologies, some of the structures that Mike mentioned earlier, like FinFET, is actually a 3D structure itself. So even within a single 2D layer, you have 3D silicon being built and fabricated by these ASML machines. And I have a good friend of mine who's now leading part of the CHIPS program, Greg Garrick, that gives a fantastic talk on how those ASML machines work. But they bounce a laser off of a piece of tin that's dropped from a dropper, and it refracts just in time in order to etch the silicon. I mean, that's how complicated these systems are. It's a crazy amount of complexity in order to get to these really small feature sizes. And then they're basically slowly building them up like a 3D printer, even just to get the 2D. And as Mike said, right now, you've got these chiplets that can then stack on an interposer, and that gives you a level of 3D. And there are companies that are looking at stacking several layers on top, usually memory. One of the problems that you start to run into is heat dissipation, right? A lot of the packaging technology, even at 2D, at these compute densities, is having a really hard time dissipating the heat. Imagine stacking even more on top and acting as an insulator. And there's all sorts of interesting solutions that people have been playing with in academia and some in industry, including at IBM, like microfluidics, where they have these little pumps that sit inside the chips and pump coolant through the silicon stack. So there's a lot of emerging technology that may drive that a little bit further. But then there's also, and that's just stacking on top of each other with these, they're called through silicon vias, which are like wires that drill down. It's the way a lot of the chiplet stacking works. But there's a step beyond that, which is closer to what I was describing earlier with the way that they're fabricating the existing like FinFET transistors in 3D, which is you go fully monolithic 3D where you just keep building that printing process like a 3D printer all the way up with your silicon. And again, you still have the thermal problems, but you get all of these advantages. So for example, if your memory is sitting on a memory chip that's way across your system, you have to spend a lot of power and wait a long time in relative time to get memory from that chip. But if you can build your memory right above you, it's much closer. So you don't have to expend as much power and you get it a lot quicker. And that's the sort of technology that's in some of the GPU memory called HBM. And there was another technology called HMC that was before it, where you just stacked memory on top of memory. And then those things could then stack up either right next to your processor or above your processor in some of these future designs and give all of these levels of efficiency, assuming you can solve the cooling problems and some of the complexity. So this is absolutely something we've been looking at for a while, partially because of the energy efficiency advantages it gives you. And it's not just in the supercomputers that we're looking at it, although supercomputers are certainly where it's being driven first. But there's a lot of advantages even in mobile because you want your battery to last as long as possible. And if you want your battery to last as long as possible, you don't want to have to spend a lot of time going to go grab that memory. And so it's pretty applicable across the stack.
Yeah. So chiplets certainly have their place, and I think as has been alluded to, being able to access them very quickly and efficiently is incredibly important. So we're looking at in our future generations deploying it, especially for HBM. If you need HBM, high bandwidth memory, it's a really nice choice. But in order to get there, the process technology has to be able to take advantage of it. And so one of the beauties of TSMC's most advanced technologies at 3 nanometer, 2 nanometer and below, 16 angstrom, they've offered backside power capability, which again allows the chip to be stacked very efficiently now because you can use your through silicon vias, access your backside power, develop your entire chip architecture very, very efficiently. And that allows you to keep the chip smaller and take advantage of that 3D space to bolt on your high bandwidth memory. So yeah, chiplets certainly have a role to play, and we're looking carefully at the emerging technologies. Keeping them cool is a huge issue. We're liquid cooling Thunderbird right now on board, and looking at some of the advanced technologies that are being developed right now. Look incredibly interesting as we try to cool the parts that are running now at speeds that were unprecedented, and their computational capabilities are enormous. And so looking at alternative solutions for cooling is going to be just as important as figuring out how to stack them and how to continue to gain Moore's law, how to continue to put more in a smaller space and have it run at a higher bandwidth than previously.
Great. So I hope everybody's got a feel for the fact that there are really talented people working on techniques to lay out transistors and even use the third dimension spatially to try to get more and more potential performance out of these and ensure that we're able to continue with the exponential increases in performance that we've seen, as Mike mentioned at the beginning, for decades. I'd be remiss if I didn't point out that all of us here have really targeted our answers towards the leading edge of the chip sector. There are chips that cost dollars to make. There are greeting cards that will play a song when you open it up that have chips in it, and you throw the greeting card away after you've heard maybe half the song. So we can make chips very inexpensively that do very, very simple things. But what is pushing the state of the art, what is pushing the envelope, is trying to make chips that can do ever more complex things, more powerful things, and keeping the cost down and also keeping the power down. And Thomas got to that with his answer there. We haven't really talked a lot about power consumption other than some opening remarks, but with power consumption comes heat. Heat is all the power you put into it that didn't do what you wanted it to do, computation, but there's always going to be some heat, just like an incandescent light bulb produces a lot of extra heat. LEDs only a little bit. We want these chips to be as efficient and do a lot of computing without generating much heat, but we ask them to do so much, they generate a lot of heat. With that, I'm going to move in a different direction, and we're going to go geopolitical for the next two questions. How important are the international restrictions the U.S. puts on selling these processors, and how much are they heated, and can you describe them a bit? For example, you mentioned that these fabrication locations are in different companies, but the IP is mostly in American companies. The NVIDIA IP, the Intel IP, the AMD IP. So it's still US companies determining how the circuits and transistors get laid out for maximum performance and then putting regulations on which processors can be sold elsewhere. The cell phone processors, sell them anywhere in the world. But can you describe the state of the regulations about selling high-end processors, and how does that evolve over time if the chips keep getting faster and faster?
Yeah, so the government bureaucracy is trying to wrestle with this and figure out how to regulate the performance of what can be sold to China, basically. And they try and put out some regulations, and a lot of companies, AMD, Intel, NVIDIA, then try to produce lower performance versions of their chips to sell to China. And in a couple of places, the US government comes back and says, nope, not low enough. Take some other stuff out. We have to go back and redesign the chips and make them even lower performance. So that impacts our sales for all the high-end companies. But it keeps getting done over and over again. And the government bureaucracy keeps trying to figure out what makes sense here as things get more and more powerful. How effective is this? We sell chips to someone in Europe who sells them to someone in India, who sells them to someone in the Middle East. And before long, engineers in China are working on them. So there are cases where we know the most advanced chips in the world do get leaked to China. We just try and minimize that as much as possible.
Anything to add down there?
Yeah, so there's a couple of things here as well. Predating performance in silicon being export controlled, cryptography was also export controlled before it. And that affected all different segments and still does. And similar sorts of things had to happen where there was then a China version of the cryptography that was incorporated that would be natively developed in China. And that became a lot easier in IP ecosystems like ARM and RISC-V because they could integrate that IP as a component. The politics are really complicated. Also, ARM's technically a British company, not a US company. That's true. But owned primarily by a Japanese company. But,
That's a good point. I should have added that companies making processors like NVIDIA out of ARM IP is a US company, right?
But you know, we've struggled with this a little bit, just like everybody else. Actually, there's an even deeper amount of stories, which I'm not sure how much I'm going to go into. But for a while, what China was forcing a lot of companies to do was to actually have a subsidiary in China that was 51% owned by the Chinese. ARM had such a company that was fraught with some challenges. AMD was Hygon, is that right, Mike? I can't remember the name of it. And several other semis had sort of the same thing, where they had to have a majority-owned Chinese subsidiary, and partially because predating US getting chips and EU having their version of chips, China was dumping billions and billions of dollars into their native semi companies. And as the US started to wake up to this as a threat and started to put export controls in place, the Chinese just started dumping more money into it. And it actually caused an explosion of new companies in China that now compete with the West in these areas. So export controls in some way made it worse in certain ways. And actually, the biggest benefit of that was actually the RISC-V ecosystem, because most of the Chinese architectures are RISC-V based that are coming out of that, because even the ARM architecture is export controlled in some ways. But since RISC-V is the instruction set is managed as a Swiss company, they truly are a Switzerland architecture. And so far the Swiss haven't been pressured to export control vector lengths and things like that for that particular architecture. But what that did is that created, before we had somewhat of a control point in that we controlled the manufacturing and the export of chips. But now China has RISC-V as an open architecture, and they can build whatever they want out of those. And now they're getting fab capacities up themselves because they've invested hundreds of billions of dollars. So Whether or not all of this will work out in our favor in the long run is a really hard question to answer right now. I think any solution here is going to have different problems in terms of international competitiveness. Computing has become the strategic asset, and AI is even more in that capacity, not just from a military standpoint, but even from a commercial standpoint. And all countries see that. And that's why you see not just China developing a domestic ecosystem, but Europe has the same thing where they're trying to dump money into reigniting, having a better domestic silicon supply chain. India, same thing. So this is becoming a big issue for all countries because no one wants to be cut off. And even though right now export controls from the US are primarily targeting China, historically they've even been targeted at countries that we would consider friendly countries. And there's lots of politics behind that. And you don't want technology to turn into a political weapon.
Yeah, the geopolitics have become very layered in this particular arena, and there's no real clear answer right now. The difficulties lie both in China's ability to take designs that we take and copy them, but it also lies in the fact that they're developing a lot of process technology themselves. SMIC used to be kind of an afterthought as a wafer fab facility, but the Chinese government has poured billions of dollars, and now they're not state of the art, but they're just a couple of nodes behind. And so they can take state of the art technology developed here, developed elsewhere, and incorporate it into their own ecosystem. And so how that gets regulated is very, very complex. Our import-export controls are trying to do the best job that they can, I think, at some level, but they're being driven by the administration that's trying to walk this fine line between being creative and allowing technology to flow back and forth between countries and protecting the proprietary technologies that are developed by US-based companies like mine. And they're even targeting RISC-V now. I mean, they're concerned now about extensions and instruction extensions in RISC-V, and they want to regulate that to try and keep it out of China. And so it's hitting us at every level, and it's going to take some really, really brilliant minds to come up with ways that will allow us to both protect our architecture, protect the proprietary nature of what we've developed, but allow trade to go back and forth. I mean, the BOM I'm building right now has a tremendous number of Chinese components. If tariffs go into effect, it's going to cost us a heck of a lot more money to build this product if tariffs get put on imports from China. And so there's no easy answer, and there's no single answer that is going to make everyone happy. So we're just hoping that we can come up with solutions that at least address the issue at its rudimentary level and protect the IP we've been creating.
All right, thank you. I'm going to follow that up with a quick answer question, I think. On a scale of 1 to 10, how concerned are you about China's position on Taiwan, that it believes it's part of China, and the constant balance of the threat, the military threat that's there? So answer that on a scale of 1 to 10, and also on a scale of 1 to 10 or more, how long do you think it will be before the U.S. again has the most advanced manufacturing technology for microchips in the world, as we used to, but no longer do? So each of those is sort of a 1 to 10. At least I hope the second one's within a 10.
Well, the first one affects my company a lot directly. So on a scale of 1 to 10, I oscillate between a 6 and 11 based on what I see in the evening news that night. If China invades Taiwan, knocks out those plants, AMD is screwed, NVIDIA is screwed, Apple is screwed. They all get all their high-end chips there. You might want to go out and buy a lot of Intel stock, though. Eric?
Yeah, it's one of those topics that I don't want to answer on anything that's being recorded in some ways. I do think that, you mentioned SMIC coming up. As China develops more of its own native capacity, I think the technological threat of a incursion in any place in the world, right, lowers a little bit because they've got less incentive to do it. The downsides start to become much worse than whatever gains they might get out of it from a technology perspective. But politics are politics, and sometimes people do things for stupid reasons. And it's one of the problems of being in a global economy. Our supply chain is really fragile, as the pandemic taught us. You know, I think it is a concern, and I think having a diversified supply chain that's international is the best approach to dealing with those issues.
You know, the early part of my career was all spent at Motorola, where we competed directly against Intel. So I've never rooted for Intel in my career until now. Okay. We need Intel to be strong and to continue to be a technological innovator on the wafer process forefront. The other thing that I think helps me sleep a little better at night is the fact that, you know, wafer fabs like TSMC are now building factories on US soil, right? So TSMC is building two 5 and 4 nanometer factories in Arizona, and they've committed to a third, and I heard of maybe a fourth.
But not their most advanced node.
5 nanometers, not the most advanced node, but it's pretty bleeding edge still. You know, 5 and 4 nanometers right there. So it's not the most advanced node, but their next generation factories, they've made a huge commitment to try to assuage some of the concerns that we have about the geopolitical tensions with the mainland. And so I think as we see more of that, and we see, you know, more, I think, results from the CHIPS Act, we see more memory, wafer fab capacity being stalled in the U.S. So we're onshoring a bunch of this fab capacity that used to be all completely offshored. And so while, yes, I'm very concerned, and it does keep me up at night, I feel a whole lot better about the direction we're heading right now.
All right.
Quick, there's comments. There's interesting discussions about what they would do with those plants in Taiwan if China invaded. Some people were speculating that, yeah, this is interesting, that Taiwan would actually blow them up before China can get them. And if they don't do that, there's some speculation, would America bomb them before China gets them? But it turns out the people who work at the plants say they are so hard and delicate to keep going. There's many, many ways to sabotage them. Don't worry about it. The people who build the at ASML in the Netherlands, who build the key equipment, said, "Oh, we've got kill switches. We can knock them offline remotely. Don't worry about this. China will never be able to use them."
That doesn't really help with the supply chain disruption,
Yeah.
though. And the other thing to point out, you brought up the memory. And I may be wrong on this, but there's a large portion of the memory fabs that are in Korea, which also has a very volatile neighbor.
Indeed.
And so that could be another area where there's a huge potential disruption that we would have to worry about.
Well, let me bring it back to a final question for me that's positive. In sort of 2 minutes or less, because we're running low on time, what advice do you have for CEOs or CIOs that are having to make purchasing decisions that, you know, for on-prem systems are 5-year systems in many cases, plus or minus? So what advice do you have now about making architectural decisions, chip-based decisions for the kind of systems they're going to deploy? And with all these AI upstarts and everybody developing new optimized chips for AI and other workloads that may come out, is now the time to keep one foot in the cloud door so you can experiment with a lot of different chips? Is it better just to go all in on something? What is your sort of summary advice you'd give to a company with a pretty big budget that needed to build a very large system for compute workloads over the next 5 years?
Good luck. I think you have to keep your vision. You know, whatever you've set out to do, whatever, you know, your company is trying to produce, you've got a long-term vision. And I think you have to look at all of the indices that are dynamically changing and assess all of those, and then be core to who you are. I mean, and yes, you have to adapt, you have to change, you have to innovate. You've got brilliant engineers behind you doing all of that work. But I think staying true to the vision that you've cast for your company in whatever direction you're heading, and then utilizing the technologies at your disposal to accomplish those goals, I think that's key.
So it's becoming an increasingly hard argument And it really does depend on workload, but it becomes an increasingly hard argument to bet against the cloud vendors because of the fact that they have the economies of scale at their side. If you look at the CPU volume, it is majority going into the hyperscalers now, and that allows them to get a lot of pricing power. And Jay mentioned Graviton. That's just one instance where Amazon's building their own chips and their own systems now and taking out margin from the companies that used to provide those. Intel used to make fabulous margins on selling stuff to Amazon, even with the price pressure of volume. And that's all gone now because Amazon's building it themselves and they're dealing directly with TSMC. And that becomes very difficult to compete with as a small company that's not going to have that capability, or even a moderate sized company. So, there's definitely TCO calculations you can make. But if you're not utilizing those systems 100% of the time, the economics of the elasticity and the volume in the cloud become really hard to bet against.
So I'll tell you why it makes complete sense to rely on just renting time in the cloud, and I'll tell you why people are not doing that. I talked to a guy from Microsoft who was in charge of their long-range vision for data centers, and he defined that as figuring out what they're going to do 6 months from now. So things are changing so rapidly, it's hard to keep up unless that's your full-time business, basically. And you're competing with Microsoft and OpenAI and Amazon and now Elon Musk, who are willing to put in orders for 50,000 GPUs at a time. And you'll have to get in line behind them to get a large number of GPUs. So that just doesn't make sense. However, a lot of countries around the world do not want to rely on OpenAI and Elon Musk for their AI facilities. So there's this movement called sovereign AI, where a lot of countries around the world want to build their own on-premise, in-country AI systems and run it and train it themselves and control it themselves. So that's a big trend that's starting now.
Great. Thank you guys so much for this conversation. And we're not done yet. As I mentioned at the beginning, South by Southwest is one of our great partners in the Austin Forum on Technology and Society. It was one of the inspirations for me creating it some 17 years ago. And I'm very pleased that tonight's guest moderator for audience Q&A is Amy Casolaro, the Director of Credential Sales for South by Southwest. Please welcome Amy up to the front. Amy's going to pick out 3 or 4 questions from the audience that were her favorites that came in, saving one from a person in the room, hopefully, for the South by Badge winner.
Hi, everyone. Great to be here tonight. Yes, I'm here representing South by Southwest, that little festival and conference that takes over Austin in March. Hard to believe we are already talking about it, but as we know, time flies and it'll be March before we know it. So I've been with South by for about a month. So still pretty fresh and learning and meeting everyone, but I'm excited to be here representing the company. And thank you, Jay, for having me. Lots of really great questions. I have a few that I have starred in the chat, and I'm gonna just dive right in.
Quick answers too, so we can get through.
Quick answers. Are materials other than silicone being considered for future type of chips to help improve performance and solve problems traditional chips face?
I can go. Yeah, there's a lot of very exotic materials beyond silicon being looked at. They're sarcastically collectively known as unobtainium. But one of the interesting things is actually carbon replacing silicon. So we could, in the future, next decade, have carbon-based intelligence systems competing with us.
There's a ton of different things that go into the process. And some of these have very crazy chemical compositions, and there's carbon nanotubes and so forth that are being incorporated into potential future chip designs. At the other end of the spectrum for performance, one of the things that some colleagues of mine are working on that spun out from ARM is a company called Pragmatic. You know, I described the 2D and 3D layer as being sort of like a 3D printer. They're literally using inkjet printers to print chips. And they're these light bulb class of chips. They're not very powerful processors, but they can literally print them using an inkjet process. And that makes things like RFID chips and NFC chips and really simple microcontrollers fantastically inexpensive. I talked about, 700 million to build a high process chip. These you can build for cents. And rapidly innovate on designs because it's just run it through the inkjet printer again, and only some of them catch on fire.
Yeah, the problem with silicon is it's so cheap, right? It's the most abundant substance on the earth, and being able to use it has benefited the semiconductor industry since its inception. And so trying to find a replacement, I mean, they've used gallium arsenide, obviously, for power semiconductors, which is a rare earth metal. But it's expensive, even in the quantities we use it. And as an industry, we use it a lot, but it's still expensive compared to silicon. And so trying to find a replacement is daunting, but there are physicists at work, as we've discussed, and we don't stop looking for solutions, because at some point it will run out of steam. We'll have to find a different base level element. And so that physics work is ongoing.
Great, thank you. Next question. As discussed earlier, there are 2 Moore's laws related to manufacturing and the doubling of costs every 2 years. Should there be, or is there already, an equivalent limit, restriction, or at least consideration based on ethical and environmental considerations, from mining materials and labor conditions to the ever-growing e-waste?
Well, there's certainly a big concern on the power requirements and the water requirements on some of these, and the implications of that to climate, both in terms of the carbon footprint and the water footprint. I'm wanting someone to figure out, every time you do a Chat GPT query, how much water is that actually using? Is that a cupful or more or less? I don't know yet.
So there are a lot of emerging sustainability goals within the industry. Some of those SRC things that I talked about earlier, and Jay's going to put up links to, have vast chapters on it, including manufacturing byproducts and things like that as goals. There's also the energy problem. The current curves show us eclipsing the total output of potential power Earth could ever generate if we stay on the same trend. And obviously that's not sustainable. So I think and energy efficiency in these systems is becoming the real limiter. There's only so much power you can pump in. You're hearing stories about data centers buying power plants and investing in power plants in order to supply them. But there are always going to be limits there. And so we have to find ways to be more efficient. In many of the high performance computing systems, when you're running the LinPack workload, you're running at somewhat peak efficiency. But when you run the average workload, those gigantic systems like Frontier are running at 5 to 7% utilization. And the rest of it is wasted, but it's not really wasted because the performance comes from the speculation. So we have to do better, not just in the way that we're building the systems, but the way that we're developing code for them and running them to increase those utilization factors so that we're not using as much power.
Yeah, and the power utilization and the environmental impact of having to supply the power to all these supercomputer data centers is hugely on the forefront of everyone's minds, right? It's at the forefront of what we're doing at Inspire. It's at the forefront of what I think we as a society are trying to accomplish in terms of reducing our overall carbon footprint. So yeah, it's factoring at a huge level into what we're doing with Thunderbird. We're trying to deliver twice the performance at half the power, and that half the power is really, really key, right? So that's the focus. And as we continue to march down these technological paths that are going to open more gateways and more ways for us to be more not just power conscious, but more efficient in the way that we process and handle these heavy data workloads. And so that's where a lot of the engineering challenges come from.
Okay, just for fun, how far away are we from having a smartphone that can last a whole week, like an old school Nokia, without increasing the battery size and reducing performance?
Oh, it's the reducing the performance, that's the catch, right? And maybe we don't have to reduce performance, but I'll give you an e-ink screen that doesn't change as opposed to your high quality OLED that you can watch Netflix on. The trade-off, the power use in most cell phones is actually mostly in the display and the radio, not in the processor technology. And so a lot of what gates that sort of achievement is improvements in those areas, as well as improvements in battery, which we continue to try to aspire to in lots of designs. But the really hard thing is that AI is somewhat driving things in the other direction, because inference on your cell phone does use a tremendous amount of power, not just in the processing power, but in all the data movement through memory. So it ends up being counter concerns, I think. Nokia's lasted a really long time because they had really simple displays and weren't really doing much.
Yeah, as consumers, the more we the more we have, the more we want, right? So you never stop wanting your phone to do more, and as you want it to do more, it takes power to do that. And so the industry is always trying to find more and creative ways to solve that power performance demand by consumers. And miniaturizing it also costs power. So making it small, efficient, and extending battery life in the same form factor is a three-way challenge that the mobile industry has been facing for years. And I don't think there's the more the consumer has, the more they want. So even if we found a way to bolt AI onto a phone and not have it increase in power, but not have to get a bigger battery, tomorrow we're going to want something new and different. So it's an ongoing challenge.
So the answer is sorry, not for a long time.
Okay, this is going to be the final question and what I have dubbed the winning question. I want to make sure, though, that Joshua Mora, are you in the room? Hi. I just thought this was a really great question and super relevant for this forum and community and conversation tonight. It's a little lengthy, but we're going to go for it. So, being a forum at the intersection of technology and society, a very sensitive topic is on responsible development and usage of technology. I'm not aware of formal processes in which society could participate and provide feedback, contribute, get educated, steer companies and government to the creation and uses of technology for good, and to tightly control and have technology means to protect us. Those that challenge the companies are considered whistleblowers and are banned instead of supported. Any formal and public processes and/or organizations to help support those activities.
Oh. So I'll put in a plug for the UT Good Systems program. They have some workshops and seminars coming up later this month that you can sign up and attend that address this social responsibility for computer systems exactly. And a lot of companies, including ours, are working on responsible AI statements. We're just waiting for legal approval before ours comes out. But the effort is there. You can question how effective it is. I think a lot of it's going to require some legislation, and that's something being experimented and struggled with right now.
Yeah, I'll give a point example of something we're involved with, but along with a number of other technology companies. There's an initiative that's being pushed out of the government called C2PA, which was originally about tracking the provenance of data, mostly in the form of pictures and articles, so that you could identify, or video, so that you could identify if something had been manipulated. And so it was basically a source to sync tracking. So if you put it through Photoshop, it gets tagged securely and cryptographically that this was modified by Photoshop at some point, and here's the person that modified it. And the consortium of companies that were doing this were a vast array of companies that kind of control that whole chain of information. And so there'd be a way to authenticate content. That's now pivoting into AI-driven sources of training and also being used to tag AI-generated content. So it's one of the mechanisms that can be used to police inappropriate use of this technology in terms of generating misleading information or false data or whatever. And so that's an area where companies are right now willingly banding together to try and have these responsible, ethical approaches to how we can control the technology by using technology to police itself.
And the training models are obviously gathering data off the internet. And so you've got all kinds of copyright and proprietary issues that are coming up from data that's collected by the training models that wasn't purchased, it wasn't paid for. It's being used and exploited, but there's no compensation. And so it's multi-layered on how that gets addressed. And I know there are several initiatives going forward that are trying to help solve that problem, but it's really complex. And it'll be interesting to see how the big AI users, especially people like ChatGPT, are going to come to terms with how they compensate for the data they've collected. Because the rightful owners of that information are starting to take notice, and they're wanting to be compensated as appropriately. So yeah, it's a deeply complex issue right now.
All right, with that, let's give a round of applause to Amy, to our speakers, and to Joshua. Thank you. We just have a couple of final announcements. You may want to take a picture of this screen. This contains a list of some of the resources that our speakers mentioned tonight. If you're really interested in the future of semiconductor research and some of the challenges ahead, the slides will also be made available, as always, on our site. We got feedback that people never seem to know that because of the way we've organized the website. So we're going to change that over the next month. So there's a real clear area where you can find downloads for things.